quite a bit different than what we were doing before, because we were really doing like an algebraic sort of process for solving those equations. Today we're going to be looking at graphs, and we'll be looking for key features of the graph. So things like x-intercepts, y-intercepts, increasing, decreasing, concavity, all kinds of things like that. And we will only be looking at exponential and log graphs today. And if you want to keep your computer up, we are going to use Desmos some. You know, please don't be doing other things on your computer. I'm not going to. I generally don't want to have to use the class-wise other than testing situations. I could if I felt like nobody's paying attention to me and everybody is, you know, playing Tetris on their computer, trying their best to beat Jeremy Zamudio, then I could make you guys bring your Chromebooks every time and use that. But I generally reserve that just for quizzes and tests because I know you prefer your own computer, and that's fine for a lot of you. But make sure you're with me on this stuff. So, for our notes right here, I'm going to draw in on this graph, although I've not done a very good job of drawing it, the line y equals x. No, that's still wrong. There we go. No, it needs to go here. That's -7, -7. We need to go here. Somehow it's easier to do on paper than it is there. So I'm going to also draw this over here. So the big thing that I want to emphasize, and we've talked about it a little bit already, is that logarithms are the inverses of exponentials. So I think that it's pretty understandable what exponents are and why we would use them in certain situations. And even starting in Math 1, you do a lot of work with things like exponential growth and decay and that sort of stuff. So exponentials kind of make sense to us what is happening there. Logs are the way of dealing with exponentials, the way of undoing exponentials, because logs, each operation that we use needs to have an inverse. So like some of those are really simple and we're really familiar with them, like addition and subtraction. We don't even really think about that because it's so elementary, right? But if you are going to be able to add things, you also need to be able to take them away. Multiplication and division are inverses of each other. You learn how to multiply in the 3rd grade, and then in the 4th grade, you got to reverse that, right? Because some problems will require you to multiply. Sometimes you need to undo that multiplication that was done. So logs are our way of dealing with the exponential. Because if we can raise something to an exponent, we also need to be able to undo that raising of the exponent. And if you have something like, for example, right here for this problem, this one is the graph of y equals 10 to the x power. Right? So that blue graph for your first graph, that is y equals x to the 10th power. See, I'm sorry, I'm saying that backwards. I've written it correctly. 10 to the x power. Okay, so that is an exponential. We can't deal with it. You know, if we've got 10 to the x power equals 9, we can't deal with it the normal ways we would deal with things with solving equations. We can't divide by 10, because what does dividing by 10 undo? Multiplication, right? Not exponents. Exponents is repeated multiplication. So we have to have an operation that will undo that repeated multiplication, that raising something to an exponent. And that is where logs were developed. So whenever you're thinking of a log, you know, if you've got something like 10 to the x power equals, let's do something where we could actually figure it out, equals 100, right? The log is saying 10 raised to what power would equal 100. Like, we know how to do this one because 10 squared would be 100. But a lot of times it's more like this, 10 to the x equals 9, like I just had written. And we don't know what number that would be, because 10 to a power equaling 9, there's a number that it will be, but we don't just know off the top of our head what that is. But if we use a log, there, then we can solve that. We're going to get some number here. What do you guys, somebody want to type that in for me? We do log 9 over log 10, or well, actually, log base 10 is common log. You just type in log 9, 0.954, and so on. So, and that makes sense because it should be a little bit less than 1, right? 10 to the first power would be 10. That should be a little bit less. So logs are our inverses of our exponentials. So let's talk about what that looks like on the graph. Okay? So on the graph, this is my graph of y equals 10 to the x. Okay? There are not a lot of points on this graph that I can write in. I do have this point right here is at 0, 1. I could put maybe, for example, this point right here. It would be, my x-coordinate would be 1. I'm sorry, negative 1. If I've got 10 to the negative 1, we talked about this just a little bit. What do I have to do with negative exponents? Move them to the bottom, so that 10 would go to the bottom. I'd have to put a 1 in the top. So this would be negative 1, 1/10 would be the coordinates of this point right here. Whenever we have inverses of each other, they undo the function. So what happens is your coordinates switch. You probably have found inverses before where you take your equation, you switch your x and your y, and you solve it again. We'll do some of that here as well, but not in this particular section. So that means like the point over here, you should see that you've got the point 0, 1 becomes 1, 0. So that's this point here. It's just like your whole x and y list switch. Over here, we've got, for this point, 1/10, negative 1. Would be the coordinates of this point right here. Okay. I really don't know what extent you go into this in Math 2 anymore. In geometry, we used to do a lot of stuff with reflections and whatnot. I think you still do some in Math 2, but I don't know if it's like it was in geometry. But what happens here is when you have inverses, the graph is reflected over the line y equals x. So basically, the information you have for the x's switches and becomes the information for the y's whenever you go from an exponential to a log, or a log to an exponential there. For this, and this red graph here is y equals log of x. Yes, base 10 is understood. The blue graph over here, I just wanted to show you a couple of these. I'm not going to talk about it much. This is the graph of y equals e to the x. Notice it has a lot of those same properties. It looks very similar. It's just not quite as steep as y equals 10 to the x. That is because e is 2.71828, right? Which is smaller than 10. So it's going to behave in the same manner. It's just not going to be quite as steep. So if this is y equals e to the x, what is the graph of our red graph here? Y equals natural log of x, because natural log is a log base e. Those would be our inverses of each other. you can see these two are also symmetric about that line y equals x. You are probably more familiar with what the graph of an exponential looks like, because I know that you have been doing those since Math 1, right? You start looking at exponentials in Math 1. So we're, especially exponential growth, we're pretty familiar with that. Starts off slow, shoots up really fast. So logs are basically when we take that and flip it over that line y equals x. So we should be able to recognize these functions as being exponentials or logs kind of by looking at them, or at least having a good guess about what they are by looking at them. So let's look at some of the stuff that we are going to look for. And we are going to use Desmos here. I'm going to go ahead and I'm going to split screen mine. I like split screening this so I can look at my notes and my Desmos at the same time. You guys probably don't need the split screen because you're not writing on your screen, but it may make my graph a little bit different than yours. Make this a little bit smaller over here. Okay, so key features. You should have talked about this in your classes before. Domain. What is domain going to be? Those are your x values. Okay, I believe right now is when Coach Wood would break out into all my x's live in Texas and tell you that since his x's live in Texas and Dallas is in Texas and Dallas starts with a D, which stands for domain, so domain is x values. I mean, that's a clear path to understanding why domain is x values. I think, it makes total sense why you would do that. So, domain is your x values. Range, what's that going to be? Y values. Okay. So, for these problems, we are going to use Desmos for our graph. Whenever you see this one on a quiz or a test, I believe what I have done is I have not made it calculator active, but I have put a picture of the Desmos graph there. So it's not like you can type things in, but you'll see the picture of the graph there. So if I look at y equals 2e to the x, I have this graph right here. Okay. So when I look at x values, let me just put x equals a right here and put a slider in. Why is that not doing a slider? I don't know why it does that. I'm going to do -10 to 10. Okay. All right, so if I think about x values right here, the question just is, does my line exist for that x value? Right, over here, clearly, I can see that I'm touching, I've got an x value for all of these. What happens over here? Okay, it goes off of my graph. My question is, do I have a vertical asymptote for this? So have you guys heard that term asymptote before? So if I were to zoom out enough, and the way I'm going to do this, I'm going to go to my y-axis because that's what I need to see more of, and I'm going to do 100. Let's see. I'm going to make this full screen so we can see it a little better. I'm going to drag this over here. Okay, let me do this. I'm going to go to here, my y-axis. I'm going to make it 100. I'm going to just keep putting some zeros and see if eventually I can put enough zeros where I'll see it cross. I can, all right? So if I slide this over further, it doesn't look like it touches. But if I add another 0, right, I can see it does eventually cross. So what this is going to continue to happen, okay? So the domain for this one would be, I'm going to use both interval notation and inequality notation. Okay, so for interval notation, I would do -∞ to positive infinity. And this is what you took notes on last night. I think that that Miss Martin and Coach Wood are using interval notation more than they used to. So you're probably, have you guys seen interval notation like this before? So it may not really even be necessary for me to go back over it much anymore. For this, I would say all real numbers. There's not really an inequality notation for this. All real numbers has a mathematical symbol. It is an R with a double bar like that. So you can write that. It's a mathematically accepted symbol that means all real numbers. So our mathematicians like to write as few words as possible. So they make up symbols for words so they don't have to write them anymore. So domain, interval notation would be negative infinity to infinity. Inequality notation, you would just say all real numbers for that because it's everything. So put yourself a little note here. Domain for exponentials is always all real numbers. Okay? There are some exceptions if you have crazy stuff like 3x or 3 to the x squared minus square root of x. If you start putting other types of functions in your exponent, there might be some exceptions to that. But we will only be looking at ones that just have an x as their variable, or maybe like an x plus 2 or a 3x, but nothing that has like an x squared or a square root of x as their variable. So the stuff that we're going to look at, our exponentials, are going to have a domain of all real numbers, okay, every time. So every exponential I see, I can just know its domain is all real numbers. The range for this, when I start thinking about range, I want to think about y values. I'm going to hit the house button over here on Desmos to go back. I'm going to change that x equals 10. I'm going to change it to y equals, and use the slider here. Okay, so for my y values, range is the only time I want you looking at the y-axis. We're going to see we only look at the x-axis. For everything else we're going to do. But range is y value, so we need to look at y-axis. I have, obviously, the function exists for all of these values. If I zoom out some and keep going up, it looks like this graph is going to just keep going up forever, right? So up here at positive infinity, I think we look good. We're going all the way up to positive infinity. That's the highest that we go. Now, as far as the lowest that we go, it really doesn't look like we drop below 0 right here. It looks like this bottoms out. If I zoom out some more, if I zoom out too much, it's going to look like they touch. But if I go over here and zoom back in, they're not touching anymore. So, also, like if I want to look, it looks like it hits 0. But if I keep zooming in, you can see like it's getting closer and closer and closer to 0. But it's not actually ever getting to 0. Like the more you, it looks like it hits right here. But the more you zoom in, it's not really hitting that x-axis. It's just getting closer and closer and closer and closer and closer to the number, right? So this is what we'll call a horizontal asymptote here. So for our range, the very lowest we ever are going to see this go is 0. Does it ever reach 0? It doesn't, because if I cannot, when it looks like it's hit 0, I can zoom in some more, and it really hasn't hit 0 yet. So if I don't actually get to 0, what should I use for my interval notation? Parentheses. Parentheses means that I do not actually include that value. If I hit 0, I would use a bracket. And then this goes up to positive infinity. Always use parentheses with your infinities because you can never get to infinity, right? We had a battle of infinities in here the other day after school because Caleb, Miss Davis's little boy, is in 2nd grade. Sometimes he comes over here to play with Henry after school. And they had both drawn pictures, and they were grading their pictures with numbers. So they, of course, were trying to win. So Henry started off with he gave himself like a 99, and then Caleb gave himself 100, and then they just started putting zeros on the ends of their numbers until they went all the way across the board so that they could win. So I tried to teach them about infinity, but they are in kindergarten, 2nd grade, so I don't know if they were really getting me on the concept of infinity. But they could always add one more zero, right? So you can't get to infinity, so you always use a parentheses with infinity. Another nice thing to know, for domain and range here, you're going to have parentheses for both of these because you're going to have vertical, you're going to have asymptotes. All right, so if I was going to use inequality notation, okay, this is from 0 to infinity, so it's everything bigger than 0, right? Let me go back here. So we're starting down here at 0. We're going on the y-axis all the way up to infinity. So those numbers are greater than 0. So we would have y is greater than 0. I don't use the or equal to for my sign because I never actually touch 0 because it's a horizontal asymptote there. Let's make ourselves a little note right here. Range for exponentials is always restricted. So you should always have a horizontal asymptote somewhere for these. Sometimes it's a little hard to tell with the graph because exponentials are so steep. Like if I really zoom out right here, it really looks like that exponential might also have a vertical asymptote. It does not. Exponentials always have horizontal asymptotes. They do not have vertical asymptotes there. But sometimes it's a little hard to see from the graph. So let's go on to our next one. We got 5 log base 3 of x. So if I go over here and graph that one, 5 log, what was it? Base. How was it you said to get down to the... Oh yeah? That way I do not like having to go that function menu.
Yeah, it drives me crazy.
Alright. Was it log base 3 of x? Yes. Alright, so here is my graph for my logarithm. If I put in an x equals line here and have a slider again. So, let me get back. House button so I can see this a little bit better. So if I, let me make this go up to down. Alright, if I go over this way, I can see I've got a graph over here on this side. It's going to keep on going that side forever. But if I go over this way, am I going to have a graph over on this side? It does not appear so. And it looks like, if I zoom out, that this is a vertical asymptote because it looks like it's going to hit that graph exactly. Now, zoom out enough, it looks like it has a horizontal asymptote as well, but it will not. This is at 0, is the very lowest our x-coordinate can go. So for this one, our domain would be from 0 to infinity, or x is greater than 0. As far as notation goes, I don't care which one you give me, the 0 to infinity or the x is greater than 0, but you need to understand both. Because I may, on the same assignment, have some that are maybe multiple choice and I've used interval notation, and others that are multiple choice and I have used inequality notation. So at this point, I just need you to be like fluent with both so you understand them both. I like interval better. I think it's easier to use. But we'll need to know how to do both. Now, my range here, so now we're looking at y coordinates. If I go and look here, as I change this. Now, if I go like right here, it looks like I never hit that line for my graph. But if I go like I was doing before and change my x-axis and make it, like 100,000, 10,000, 100,000, eventually you can see I got that line to cross that value, right? And then even if I move it up even more, if I add some more zeros, takes a few, but I can eventually get it to where it's crossing that line as well. So it may not, it kind of looks like it flattens out, but it does not. So my range for my log function here is negative infinity to infinity, or just all real numbers. Now, I said logs and exponentials are inverses of each other. I also pointed out that when we have logs and exponentials, if I have a point xy over here, I can switch it, and that's going to be on the other graph, right? Yx will be there. Notice what has happened here. For my domain, I got all real numbers. And I said domain for exponentials is always all real numbers. For my range over here, I got all real numbers. That is because the x's of an exponential become the y's of a log, right? So it is also safe to say here the range for logs is always all real numbers. And it is also safe to say here that the domain for logs is always restricted. This will help particularly when the graphs are hard to decipher. Okay. Questions on this stuff? All right, let's look at some more key features. These are pretty straightforward right here, and they're super easy to find on Desmos. This over here. I'll be able to do this will be full screen. So, x-intercept is where the curve crosses the x-axis, and our y-intercept is where the curve crosses the y-axis. Now, with a Desmos graph, it's very easy to find. You're just going to type in y equals 6 natural log of x minus 4, and you will see that you can just graph this, and you can see your intercepts. This particular problem only has one intercept. It has an x-intercept here. So we would say that we have an x-intercept at 5, 0. And no y-intercept. Now, you may possibly run into this either without a calculator or where you can't find the exact value from the graph very well. If I'm letting you use Desmos, then you're not going to have to worry about it. It'll be really easy to find. If I've just given you a picture, it may be a little harder to find. So, on my x-axis, when I hit the x-axis, what is my y-coordinate? It is 0, and it is always 0, right? So, for the x-intercept, y equals 0. This is true for all functions, not just exponentials and logs. It is true for lines and quadratics and anything, right? That's just a property of the coordinate plane here. And then so when my y will have a y-intercept, my x equals 0. So we're going to go through this in case. If I need to find it by hand and not just looking at the graph, which both are valuable there. If I want to find my x-intercept, plug in 0 for y. And so 0 would equal 6 natural log of x minus 4. And if I want to solve that, I would divide by 6. So 0 would equal natural log of x minus 4. I've got to get rid of that natural log. How do I do it? E to the power. Connor, what is e to the 0? It's 1. It's so tricky, isn't it? It seems like it should be 0. But it is 1. And that gives us x minus 4. And then we could add 4. So 5 equals x. So, obviously, Desmos is easier for that. If you see this on an ACT problem, use Desmos. If you see this, and I'm allowing you to use Desmos, do that. But we like to have a lot of tools in the toolbox to see like how everything works all together. I think it's one of the coolest things about math, how like I can see it on the graph really easily, but then I could even take that and just use it with the equation to figure it out, or you can use tables. It's pretty cool. I love that sort of stuff. If we want to do the y-intercept by hand, this one's a little bit different. We're going to plug in 0 for x, which will look like this. Y equals 6 natural log of 0 minus 4. And that's 6 natural log of negative 4. And what did I warn you guys about with logs? Can't have that negative. So this would be no solution here. Yes. Yeah, no solution. Or I think technically this like zero with a line through it is called the empty set, but it means there's no solutions in this set here. So there's no y-intercept for this one. All right, questions? So, sometimes you can tell it really easily from the graph. Sometimes you can't, and then you could use this as your backup plan if that's the case. Okay, so next thing we're going to look at is positive and negative. Okay, so positive is going to be when your y coordinates spelling here. Oh. Y coordinates are positive. And if I think about the graph, if I have positive y coordinates, where does that fall on my graph? Above the x-axis. So the opposite of this is going to be true. My y coordinates are negative for these, and that's when we'll have below the x-axis. So let's look at this function. Y equals negative 2 log base 8 of x plus 1. Okay, and I am going to do that. Put this over here just so we can see it. You like to be able to draw on the picture. All right, so it's really important. The only time you are going to look at the y-axis for any of this is whenever it asks you for range. So every other time, you need to be thinking about what your x-axis looks like. You're given all these values coming from your x-axis. So something that's very helpful for this first is to find your domain. So for this function, I want to think about what my domain would be. It is a log. Logs have vertical asymptotes. They're always going to have their domain restricted. All right. So what is the furthest left I can go on this graph? Looks like it's right there at -1. All right. So -1. And then what about furthest right? It goes forever to the right. So we'll have positive infinity. So it is always helpful to find that domain first, because your answer for where this function is positive can't go outside of that. Because this function is not going to be positive at -5, because that function doesn't even exist at -5, right? It's not even there. So if you start with your domain first, that gives you your parameters that you're working within. And the good thing about these is they're only going to switch from positive to negative one time if they switch at all. Sometimes they don't switch. But, well, is that true? It can be. Actually, logs will always switch. Logs will always switch because logs have vertical asymptotes. So they are going to go up forever and down forever. So they will eventually cross the x-axis somewhere. If it doesn't show up here, it's somewhere it happens. Exponentials may be all above or all below the x-axis. So if we look at where our graph is above, we're looking at this section, right? But we're reporting the x values where this happens. So if you want to think about taking vertical lines, right, and sectioning that part off. So if I'm taking vertical lines and sectioning that off, here, let me use a different color. The furthest left I can go is right here, because the function stops at -1. And then all the way up to that x-intercept, which let me click over here and make sure it is 0, 0. Yeah, 0, 0. All the way from here to here, I have the function is above. I'm given those x values. So my function here would be positive for -1 to 0. All right, my x-coordinate here is -1. My y-coordinate here is 0. I definitely want to use a parentheses with -1 because that's a vertical asymptote. I never actually get there. I'm also going to use a parentheses at 0 because at 0 right here, my coordinate is 0, 0. Is 0 positive? Is 0 negative? It is not. It's neither one, right? So you're going to use a parentheses with it as well because you're not positive at that point. You're neutral in that case. So you don't include 0 either. So I could also write this as -1 less than x less than 0. So when you're going from a number to a number in interval notation, you want to put your lowest number first. Always use less than signs. If you need to include the number, you would put an or equal to. Like if you had a bracket, you would use an or equal to sign. We're going to see we don't use the or equal to signs very much with logs and exponentials. It's usually a less than. All right. Then I would look for where this is negative. And that is going to be this part of the graph right here where I'm below the x-axis. So I'm thinking about, again, sectioning this off with vertical lines. So the left-hand parameter that I'm going to have here is going to be at 0. Where's the right hand? Where's it end? Infinity. All right, so this would be from 0 to infinity, or when you go to infinity, that means it needs to be like greater than or less than. So this would be x is greater than 0. Now, let me show you what, I'm going to try to show you what students do wrong on this. Okay? A lot of times I see this. So this is wrong. Don't write it down. But when they do positive, they'll do infinity to 0. And when they do negative, they'll do 0 to negative infinity. They're looking at the y's, right? But it's so easy to get sucked into doing that. Like it kind of looks right. So an alarm right here, this one I can tell, actually both of these, I can tell you they are always wrong. Okay? So when you're using interval notation, lowest number must be first. So if you're looking at answer choices and you see 0 to negative infinity, that is wrong. No matter what question it asks you, because you can't go from 0 to negative infinity. You can't go right to left. You have to have your lowest number first. So both of these, I would know they're wrong because the lowest number has to be first. Sometimes maybe it even looks right. It's like negative infinity to 0. But don't look at the y-axis. You're thinking vertical lines, x-axis only. Okay? So where this hits the x-axis. Also, your domain can help. This can't go below -1. So you can't go to infinity or negative infinity over here on the left-hand side because the function stops at -1. Notice these two pieces from -1 to 0 and 0 to infinity. If I put them together, it gives me -1 to infinity, which is my domain. There. Does this make sense? Okay. All right, let's move on. The next thing we're going to look at is increasing and decreasing. Okay, so increasing and decreasing. For increasing, your y values increase as you move from left to right. I realize it's probably not good to define the word increasing while using the word increase in the definition here. I don't know a great way around it other than saying like y values go up as you move from left to right. Not the exact word. Yeah. Yeah. Sometimes they do. That always makes me mad when I look up a word. Yeah. Yeah, I know. I always get aggravated whenever I look something up, and it's like that. Someone who minds. Thanks a lot. That's not helpful. Then you got to go look that word up. And sometimes it can be like a string of things until you're really in trouble. So, and then for decreasing, our y values decrease as you move from left to right. Okay. The big thing you always have to remember is it's left to right. You always want to start at negative infinity, go up to positive infinity. It's really easy on these to want to look at the middle of the graph and go to either end. That is wrong. It's always left to right. So if we look at, the good news about this is these are really, increasing and decreasing is really pretty easy for exponentials and logs. And this is why. If I graph this one here, g of x, oh wait, g of x equals 3 to the negative x. Okay, so if I look at this graph from left-hand side to right-hand side, what would you say about this function? Is it increasing or decreasing? It is decreasing. Okay, and it's always decreasing. It's not going to, swing back up later. Which is what makes this pretty easy, because these are always going to be increasing or always going to be decreasing. So for this particular function, what would I say, what are the x values where it decreases? It decreases everywhere on its domain. So I need to know the domain for this, right? So what would the domain for this exponential be? I'm pretty sure over here that my x's go to infinity on that right-hand side. What about over here on the left? That's where I feel unsure. Does this continue to go to the left forever? Like if I zoom out, it looks awfully vertical asymptote-y there. But what did we write about exponentials at the very beginning when we were doing domain and range? What did we say for domain of exponentials? All real numbers all the time, right? So even though it kind of looks like it is a, if I put like x equals 10, negative 10, it kind of looks like it is a vertical asymptote there somewhere around that point. If I zoom out enough, if I go over here and make my y-axis 100, keep putting zeros for that, it eventually crosses it, right? So if you can zoom out enough for it eventually to hit that line, then it's not a vertical asymptote. Or the best thing, just remember, exponentials, domain is always all real numbers. So this would be decreasing for negative infinity to infinity, or all real numbers, and it would be increasing never. My littlest one, Henry, he's difficult to deal with sometimes anyway, and he likes to yell out never sometimes, like we're riding bikes. It's been a little while back. He was at the park, and he was coming down off that little bridge, and I told him he needed to slow down because he was going to go too fast and wreck, and he just yelled out never and continued on his way. So that has nothing to do with what we're doing right now, but entertain you with my children there. Okay. That's not what I meant to do. Okay. All right. Let's look at a log. So I've got g of x equals negative 6 natural log of x plus 4. And notice, like, there are no parentheses here, so this plus 4 is kind of like on the end. Don't add parentheses in. On that. It's fine. The way it is. All right, so when I look at this, I think I have a vertical asymptote there. Where does it look like it's at? Looks like it's at 0. there. This will be, my domain for this will be from 0 to infinity. Is this function increasing or decreasing? It's going to be decreasing because as I go from left to right, I'm going down. So I would be decreasing from 0 to infinity, or x is greater than 0, and increasing never. There. Logs always have a restricted domain, so this would never be negative infinity to positive infinity for these right here, because over here at like -7, the function doesn't even exist, so it can't be decreasing if it doesn't exist. When we do these, we're going to put all of this stuff together, so you're going to find your domain at the beginning, and that will help you with some of the other parts of the question. All right. Questions here? Okay. Concavity. Rather than try to write out a definition for concavity, I'm going to draw you some pictures. Something that is concave up is going to have the smiley face shape. It's going to be curved up. For exponentials and logs, it's going to look more like this. It's going to be like half of that. It might look like this, or it might look like this, which is kind of like curved up there. So you can think if it would be like part of a U, if you were standing under it and it rained, it would catch the rain and move it away. Like, especially this one would like catch all the rain. Concave down, it's like this, like a umbrella. Umbrellas are made like this because when the rain comes down, it's going to go way to the outside. This would like catch the rain. You wouldn't have an umbrella that is like a U shape, because then you just have like a giant bunch of water right over your head the whole time. It would be effective until it got too heavy and fell and then just like covered you. Yeah, it would. I mean, it would do the same thing for a while until there was too much rain in your rain capturer. This could be a new green technology that we could all have umbrellas. This could be, we could reuse water here. No, I don't know if that will go far. If it does, I came up with that idea first. Like my husband who invented the iPhone, DVR, many things, he had the idea first. Uh-huh. Well, yeah, that's smart thinking. Yeah, my husband did not actually invent the iPhone. He just had the idea. He thinks someone may have stolen it. I mean, he thought, what if my phone could also play music, and also you have to. I am old and getting older every day, so you guys don't even know about life before an iPhone.
Well, if you did, you probably wouldn't be a teacher.
No, I wouldn't be a teacher. I mean, I like teaching, but I probably wouldn't be a teacher if he actually created the iPhone. I might come volunteer every once in a while, but I wouldn't show up every day if that was the case. All right, let's look at this. I'm going to use an X instead because it won't graph it right if I use an A. All right, so if we graph this one we have a log. Concavity is much like increasing or decreasing for logs and exponentials. Now, when we look at other types of graphs, and we will later, concavity can switch in a graph that does like this. All right. Concavity in logs and exponentials is always one or the other, just like increasing or decreasing. So it just matches the domain. All right. So for this graph, is this concave up or concave down? It's down, right? So this would be concave down. And we've got to look at our domain for this. To the left, does it go on forever or does it look like it stops? Stops. Where do we think it stops? Okay, about 1. Let me show you how we can know for sure that it is 1. What did I tell you cannot have for logs and exponentials? Negatives, right? Or 0. We can't have 0 either. So if I take what's on the inside right here, and I say a minus 1 equals 0, and then I add that 1 to both sides, a equals 1, is going to be the point where that starts to be 0, and I can't have those values below it. So if you take what's on the inside and set it equal to 0, that'll let you know for sure if you have one you're not really sure about. A lot of times you can just tell from the graph, but sometimes you might need to do that. So we're concave down from 1 to infinity, or that would be x is greater than 1, and we would be concave up. Never. All right, so we've got asymptotes, and then we've got in behavior that we've got to look at, and then we'll be done. All right, so asymptotes, you've got vertical asymptotes and horizontal asymptotes. So for vertical asymptotes, as x approaches a number, the y will get infinitely big or small. Small being negative numbers. So vertical asymptotes are those vertical lines. As we get closer and closer and closer to that line, we see that either we go down to negative infinity or up to positive infinity there. This kind of switches for your horizontal asymptotes as x approaches positive or negative infinity. So as your x gets bigger and bigger and bigger, or smaller and smaller and smaller, you will see y gets closer to a number. Sometimes I think the definitions are less helpful than just looking at the graph. This is one of those cases. So if we look at this graph, negative 3 log base 3 of 7 minus x here. Okay. So for this, it looks like we probably have a vertical asymptote here. Let's make ourselves a note right here. Logs always have vertical asymptotes. And we're not looking at exponential right now, but let's go ahead and write it. Exponentials always have horizontal asymptotes. Okay? And they will not have the other. If you have a vertical asymptote, you will not have a horizontal. If you have a horizontal, you will not have a vertical. For logs and exponentials. There are some other rules for other functions. Right now we're only worried about logs and exponentials. So this is a log. It has a vertical asymptote. Where does it look like it is at? I think it's 7. How can I know for sure that it is 7? If I look at right here, that's 7 minus x. Logs cannot equal 0, right? Inside of that logarithm. So if I do 7 minus x equals 0, I could add that x to both sides. 7 equals x. So I have a vertical asymptote at x equals 7. Remember, x equals a number is going to be a vertical line. Y equals a number is a horizontal line. It's easy to mix those up because it's opposite of the axes. All right, I know we've been taking notes for a long time today. These are long ones. We got one more thing to look at. All right, end behavior. Okay. All right, so what you're going to talk about on end behavior, you're talking about what happens on the ends of the graph. So there's basically 3 things that can happen on each end. It can either go up forever to positive infinity, it can go down forever to negative infinity, or it can even out at a number. Same thing over here on the right-hand side of the graph. It goes up forever, can go down forever, or it can even out to be a number, right? So, on the left side of the graph, what you want to say is as x approaches left, how do I say that? Left endpoint of your domain, f of x will approach, and in this blank right here, you're either going to have positive infinity, negative infinity, or a number. For the right side of the graph, as x approaches the right endpoint of domain, f of x will approach, and again, same thing here. That's either going to be positive infinity, negative infinity, or a number. Okay, so like we're going to do for a lot of these, you want to find your domain first. And your domain is for an exponential. What is our domain for an exponential? All real numbers. So okay, I can't see it, but it's because these numbers are so big. So let's make this larger. There we go. Now we've got a graph. There. So my domain is from negative infinity to infinity here. So on the left side of the graph here, as x, you can use this arrow right here for approaches negative infinity. If you, like me, don't want to write any more words than you have to. So as x approaches negative infinity, we will say f of x, or if it was a g of x or a y or whatever, we'd use that here, approaches on the left-hand side of the graph. So this is the only time you start in the middle and go out. On this left-hand side of the graph, as you go to negative infinity, what is happening to our y coordinates? Are they going down forever? Are they going up forever? Or are they leveling out? I think we can rule out going up, right? It's not going up. It's going down. Is it going to level out? I think so. And exponentials have horizontal asymptotes, so it will. X is going to approach 0. There. So that would be your left side. And then for your right side, we would say as x approaches the right endpoint of the domain is infinity here, positive infinity, f of x approaches. So on the right side of this graph, as I go to the right, what's happening to my y values? They're going up, up, up forever. That's going to be positive infinity. And that is the right side of the graph. Okay, so as you guys pack up, I'm going to pass out homework, and I'm just going to make a couple of comments on it. On the homework, please type these into Desmos and use Desmos. Also, I'm going to let you skip 3 of these. So you out of these questions that you have, you only have to do 5 because we are about out of time and you didn't need class time for it, and it's a long time. So you're going to do everything for one question, right? You're going to type this into Desmos. You're going to find x-intercept, y-intercept, domain, range, vertical asymptote, horizontal asymptote, all of those things for this one function. Then you'll type the next one in Desmos, find all of those. I won't ask you to do that on a quiz. I'll give you like single questions because otherwise it takes a long time. But for this is a good practice. Okay, so do 5 of these problems for me. You may use Desmos on the whole thing. The answer key should be posted to Canvas so you can check how you're doing with that. Okay.